Ready as I'll ever. All right. Welcome back, everyone, for ACT Math Prep. We're getting ready for the ACT Math test, for the math portion of the ACT exam. And today we're going to talk about coordinate geometry. So without further ado, we're going to get started right away. Talking about the Cartesian plane, or the XY plane, as you might have heard it called. We're going to be talking about graphing. We're going to be talking about graphing points, graphing lines, polynomials, circles, other curves, and of course try to understand the relationship between graphs and their equations. So what equations, how they relate to what graphs that we plot on the Cartesian plane. As you can see from my image here, I have our two separate axes. We've got the x-axis running horizontally. We have positive x's, negative x's. And then of course we have the vertical axis, which is what we call the y's. So we're going to start. I'm going to remind you guys, hopefully this is a review. Most of this stuff you should have at least seen already before in your math classes, and hopefully this is a good refresher on some of the things that might pop up during the ACT exam. So let's take a look at the Cartesian plane and the different parts of it. We'll move over to where we have some graph paper. And here we go. Start with some graph paper here. So the first thing to notice is how this thing is set up. So we have like you saw in the image before, we have our y-axis going in both directions. We have our x-axis, and x, there's x, and then of course this thing is gridded out properly. We have 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4 in the x, negative 1, negative 2, negative 3, negative 4 in the y. And of course, we have our very middle, we call that the origin, and we denote that xy point as 0, 0. So this is the origin, and we do our standard notation for points are usually in parentheses like this, and so x first and y second, and of course this origin point is the point 0, 0. There's other things that you should know that I've run across on the ACT test, but you should know how this thing is broken down into different quadrants. So quadrants, and of course quad means 4, and as you can see here we have 1, 2, 3, and of course this is quadrant 4 over here. So we've broken our Cartesian plane, or our XY plane, into 4 separate spots, and I want you to notice some important things to notice are the signs that go with your XYs, and each one here we have XY be positive, positive. Okay, so our points would be all positive numbers. We call this the real quadrant. Real quadrant. And that's quadrant 1, and that's because most of our real world applications happen in quadrant 1. So we call that the real quadrant. But of course we have other quadrants here. We have quadrants 2 is negative in the x and positive in the y. Quadrant 3 is negative in the x and negative in the y. And of course quadrant 4, our last quadrant, is positive in the x and negative in the y. So this is a quick breakdown of just the pieces, the detailed instructional pieces of what the Cartesian plane looks like. So we got the all important origin right in the middle, and then of course we have 1, our real quadrant, 2, 3, 4. Notice the way that it's numbered is counterclockwise. So it may be a little counterintuitive. You may want to go 1, 2, 3, 4, or go in a full clockwise circle, but notice it starts here, 1, 2, 3, 4. So we count through our quadrants in a counterclockwise order. We'll show you a little bit more about graphing points so that you understand more about where they are. Once again, this should be a review, but if I draw my Cartesian plane, this is extending in all directions to infinity, right? If I want to graph the point 3, 2, graph 3, 2, well then I count 1, 2, 3 in the x, 1, 2 in the y, and there's the point right there. There's the point that we're interested in, 3, 2. 3 in the x, 2 in the y. Similarly, we could graph negative 3, 2, and that of course would be 1, 2, 3 to the left of our origin and 2 up right there. So there it is. There it is. Negative 3, 2. Down here, we could graph another point in quadrant 3, right? Quadrant 3. How about negative 5, negative 2? Well, negative 5, negative 2 is 1, 2, 3, 4, 5 to the left, and of course 2 down for negative 2. And notice here in quadrant 3 we have negative x, negative y, and there's my negative x, negative y. So there's the point negative 5, 2. And finally, a point like 5, negative 4 would be 1, 2, 3, 4, 5 to the right, positive, and 1, 2, 3, 4, negative. You may wonder how you're going to know whether or not a number is positive or negative. If there's no sign given to the number, it's automatically assumed positive, and it will always tell you if a number is negative. So that's a quick refresher on how we graph points in the Cartesian plane and how we read this thing. We've broken it down into different quadrants, and of course the all-important origin. It's important to know that that's the point 0, 0, right in the middle. Down the road, we're going to be trying to figure out ways to perhaps find equations, right, of lines that may connect points. And of course, we're going to talk about that soon. But here you can see if I can graph points and I connect those points with a straight line, we can predict certain amounts of information using this Cartesian plane and this coordinate grid. Perfect. Just a reminder to everyone, if you guys have questions or concerns about any of the things that I'm talking about, and you want to chat with me about it, I'm available by email at inspiredclassroomtim@gmail.com. I encourage you to send me questions, and I will do my best to answer them swiftly and get you back on track, get you thinking in the right sort of mind so that you can solve some of these problems. The next thing we're going to talk about is graphing inequalities. So whenever you see these symbols here that you see, we have the little alligator symbols, right? The alligator's always chomping at the bigger bit. This the greater than symbol, this is the less than symbol, and then of course we have the equals to symbol. So we're going to talk about graphing inequalities for a minute on a number line, so in one dimension, and then we're also going to talk about graphing them on the coordinate plane. Let's talk about a one-dimensional graph, and I will show you what that looks like. So we're going to talk about opened endpoints and closed endpoints and the difference between the two inequality symbols. So anytime you hear the word inequality, you're talking about the less than or greater than things. So I'll show you how to graph some of these things on the number line. There's actually a problem on our practice exam that we did that goes with this. So let's move back to the camera 2 here, and I'll give you a quick rundown on inequalities. Here's that guy. A fresh piece of paper here. So the first thing I'm going to want to talk about is graphing. Graphing, I'm going to use blue here, hopefully that's okay. Graphing in the first dimension. So you may be wondering what I mean by first dimension. Think about when you go to the movie theaters and you watch a movie in 3D. What does that mean? It's the third dimension. It's meaning it's popping out at you. It can go up, down, left, right, backwards, and forward. So what do I mean by the first dimension? Well, the first dimension is just a line, right? So it's going to be our x-axis really without the y-axis. So there's our line. So we'll call it x. This is all the numbers on x, and we have 0 in the middle, and of course 1 and 2 and 3 going to the right, and of course to the left we have -1, -2, -3, and so forth, right? They go both directions. So if I'm going to graph an inequality, well, on this line I can actually graph stuff. I can graph, say, something of the nature x is greater than 2. Well, if I want to know all of the x's that are greater than 2, well, I want to notice first that this is a strictly greater than. Strictly greater than. So I'm going to use an open dot at 2. An open dot like that, you see? And this is what this is saying in my graph, is that I'm getting everything as close to 2 as I can possibly get, but I'm not actually touching 2. And then of course I'm going to shade the region of my graph now where x is greater than 2. So I have the open dot for the strictly greater than, and then of course I shade this way because 3 is greater than 2 and 4 is greater than 2. So this side of the graph is telling me all of my x's that are greater than 2. So this graph and this equation, or inequality rather, are matching each other. Notice the open dot for strictly greater than. Let's consider something else. How about draw this, and let's consider x is less than or equal to. So there's our or equal to symbol. So I have up here I have strictly greater than, and here I have less than or equal to. And how about we say -3? So give this some context. There's 0, there's 1, there's 2, there's 3 going in that direction. -1, -2, -3, and we're going in both directions to infinity, right? We're still calling this line x. This line is still called x. And now I need to graph this inequality. X is less than or equal to negative 3. Less than or equal to negative 3. So I'll grab my so I'm going to go to negative 3, and this time I'm going to make a closed dot. Closed dot. The closed dot is referring to the fact that I can equal negative 3 now. So that's what that's representing. The closed dot is saying that I can equal that. And of course, all the numbers that are less than negative 3 are negative 4, negative 5, negative 6. So I'm gonna shade my graph in the correct direction and solve this inequality. So this is what it looks like graphing in the first dimension. Just so you guys understand what we're looking at on our practice exam that I've sent you, if you look at number 58, so towards the end of the exam, towards the very end of the exam, we have problems, and our answer set actually looks just like our graphs that you see there. So I'm going to solve this problem for you. As you can see, I already have the answer circled. So it's not an actual graph. We can't graph this, but I will show you why the answer for this one is K, the empty set. So let's take a look at this problem. So we have, which of the following number line graphs show the solution set to the inequality? There's the word. X, the absolute value, this is the way we read this, the absolute value of x minus 5 is less than or equal to negative 1. So we have the absolute value of x minus 5, and it is less than, strictly less than, negative 1. So if I want to solve this problem, I have to have some tricks to solve for this x and get it all by itself. You may remember from our last video, I think I showed you this, to get rid of these absolute value symbols, I have to consider this equation with a positive one and a negative one. So I'll rewrite this problem. We will rewrite this problem as 1 is less than x minus 5, which is less than negative 1. So that from here to here, all I've done now is I've gotten rid of my absolute value symbols, and I'm considering both the positive and the negative. So x minus 5 is greater than 1, but x minus 5 is less than negative 1. So automatically this should start making sense about why this is the empty set. Because if I add 5 here, and what I do to one side of an equation I have to do to the other. So I'll add 5. Well, that's going to give me 1 plus 5 is 6 is less than x, which is less than 4. So I have some number between 6 and 4 where this number is bigger than 6, but it's less than 4. So what numbers on our line? 1, 2, 3, 4, 6. So x is greater than 6, so it's bigger than 6. So it's all these numbers, but it's also less than 4. So think about this for a second. Does that even make sense? Can you have a number that's bigger than 6 but less than 4? If you think about this for a second, you'll realize that there are no numbers that are bigger than 6 and less than 4. So there's a set of numbers that are bigger than 6, and there's a set of numbers that are less than 4, but there's no intersection between them. So of your choices, you may consider this guy, but but this is a graph of one inequality. So this graph right here is saying x is less than 4 or x is greater than 6. And this equation right here is saying that x is less than 4 and greater than 6. So since that's the case, there's nothing in there. So of course there are no x's that fit this equation. So therefore, this symbol right there, there are no x's that fit this equation. Therefore, that's what that symbol right there means. We have an empty set, right? Nothing in it. Nothing in it. That's not a 0. That's the empty set. So we're going to go with K, the empty set. Now keep in mind, J here was saying, J, just so you guys know, this graph here is saying x is less than 4 or x is greater than 6. This equation down here, this one here, is saying x is greater than 6 and less than 4. So not possible. So that's the skinny on that problem. If you think about it for a little while, it should make sense to you. If not, remember, inspiredclassroomtim@gmail.com, and we can chat about it some more. So that's the basics of graphing in the first dimension. It's not hard. Just try and remember open dots versus closed dots. Now we'll have to talk briefly about what does it mean to graph inequalities in 2 dimensions. So let's take a look at what that might look like. Grab some graph paper here. And this time we're going to graph in the second dimension. So if in the second dimension, the idea is pretty similar. We still have our x right here, right? We still have our x, but now we have our y as well. And before we had equations like x is greater than 2, but now we're going to have equations such that it'll be in the form of like y is greater than or equal to, say, 2x plus 3. Okay, so hopefully you guys remember y equals mx plus b, and we're going to talk about that soon in our next section. But if I have equations in this form where I can consider it y equals 2x plus 3, this is my m, so this is my slope right here, slope. And we'll talk about this some more, a little bit more detailed, but this is my y-intercept. And so now I'm going to graph this equation, and I'm going to start at 0, 0, 1, 2, 3 in the y, because that's what this guy says right here. And then I'm going to go up 2 over 1. So we're doing rise over run, up 2 over 1. And there you can see a line is forming. If I want to go the other direction, it's down 2 over 1. It's down 2 over 1. But here you can see my line. And so I'll try and draw this as straight as I can. It's not that straight. Notice my line, first off, is solid. I did that for a reason. I did y is greater than or equal to, right? So in our last one, in our one dimension, we filled in the dot to represent the or equal to part of this inequality. And here I have a solid line. If I had y is strictly greater than, say, 2x plus 3, then this line here would have been dashed, a dashed line. So just notice the two notice the two similarities is the word I'm looking for. That we had the closed dot for or equal to, and we had the open dot for strictly greater than. Here we have a dashed line for strictly greater than, and a closed line for greater than or equal to. So the last part of these graphing inequalities, right, there was on the one dimension we shaded a region, either ahead of the x or behind, and this still applies. So here you want to do what's called a test point, and generally we want to choose 0, 0, right, because it's the easiest test point. And we want to do a test point, and we actually want to plug that into our equation over here. So here I have a 0 for y, so 0 is greater than or equal to 2 times 0 plus 3. So 0, then 2 times 0 is 0, so this is basically simplifying to 0 is greater than or equal to 3. And then we think about that for a second. Is that a true statement? Is 0 greater than or equal to 3? Well, no, it's not greater than or equal to 3. So this point right here that I chose happens to make a false statement. So I don't want this side of my line. I'm going to end up shading in a different color. It's going to be either this side or this side of the line that we've created, and I've tested on this side and it was false. So this is the side that makes it true. So here's where I shade. As you can see there I'm shading with another grid. Everything to the left of my line makes my equation y greater than or equal to 2x plus 3 a true statement. So let's check just to make sure. We'll pick a test point over here on this side of our line. How about 1, 2, 3, 4? How about the point negative 4, 0. We'll test that point right there. There it is. So I'll plug that into my equation. I have 0 for y, and this is the equation I was working with. So 2 times negative 4 for the x plus 3. 2 times negative 4 is negative 8, plus 3 is negative 5. So this simplifies to 0 is greater than negative 5. 0 is greater than negative 5. So this must be my true side of my inequality. So this is how I solve this problem, and 0 is greater than negative 5, so I know that this is the side that I need to shade. So that's graphing. It's a little basic graphing in 1 and 2 dimensions. It's not very difficult. It can take a little bit of practice, but once you go through it a time or two, it should make more and more sense. And this is how mathematicians solve these problems. So we'll move on. Back to camera 1 here. People on content, perfect. Perfect. Welcome back. So that was graphing inequalities. Inequalities are these symbols that you see less than or greater than or equal to, right? Open endpoints versus closed endpoints. We talked about that. Inequality symbols. And then, of course, we talked about it on the number line and on the coordinate plane. So boundary lines are either dashed or solid, depending on our equal to or not equal to. And then, of course, in the two-dimensional part, we need to do test points. So test points are what's going to get us is going to help us solve whether or not what side of the line that we just drew is going to be shaded, and which part of that's true and which part of it's not. So if you have questions, please let me know. I will be happily answer them when I can. Okay, so we jumped ahead a little bit by graphing by graphing lines in 2 dimensions, and I had yet to talk to you about slope. Hopefully you guys have heard this before and remember from your math class the differences in slope. In the equations y equals mx plus b, the m is representing the slope. When we talk about slope, we're considering the rise over the run. Right? So hopefully you guys have heard that before and had that drilled into your brain, but it's rise over run. When you think about stairs or roofs on your house, all of these things have a slope. And we calculate them by how much it's going up versus how much it's going over. Which is also equal to the change in y over the change in x. Okay, so that's where the formula is derived from, and I'll show you this formula here in a little bit, but the change in y is the difference in the y's, and of course the change in x is the difference in the x's. Keep in mind that lots of ACT problems have slope involved, but they're represented in a story problem, so keep in mind that as a change in value, usually over time. So I got a couple of practice problems from our practice exam that deal directly with this, and I will show you here in a moment what I was thinking when I solved them. We have some tricky ones that I'll talk to you about. Horizontal lines have 0 slope. They're going straight across our Cartesian plane. There is no rise, so we have a zero rise divided by whatever the run is. It can be anything, but 0 slope is a horizontal line across our x-axis or across our plane, wherever y be defined at. And then our vertical lines have undefined slope. Why? Because they're going up and down. So think about rise over run. If there is no run, the run is 0, then we're dividing by 0, and anytime you divide by 0, you don't have a solution. So vertical lines have undefined slope because they're vertical, straight up and down, perpendicular to the x-axis. You simply go to wherever x is equal to that spot, and you draw your line up and down from there. We always read slope from left to right. Rise is positive and fall is negative. So we'll talk about some of those things in our examples. Okay. This. All right, so we're going to talk about graphing some lines. Lines are important, one of my favorite topics in mathematics. So we have a few different forms. We're going to be talking about graphing lines from equations. So the first thing I'd like to point out is that we have 3 different forms of equations. Three forms of equations for lines. For lines, we have standard form. Which is sum ax plus sum by is equal to sum c. Okay, so that's how you might see a, b, and c are just going to be numbers, right? And x and y are your variables, but you may see an equation that looks like this, of course with numbers in it for a, b, and c, but when you see that, you should notice that there's no powers on the x, and you can manipulate this into a different form that makes it a little bit easier to graph, but this is just the standard form for the equation of a line. You may also have seen a point slope form, where that's going to be where we have some y1 minus some y will equal some m. So there's our m for slope, right? X minus x1. I may have I may have, this might be y1, so this is strictly y. But here once again, if you see this form, point-slope form, you're going to use this when you've been given a point, and it's going to go right here, right? You're going to put your x1 and your y1 in right there, and then of course you'll be given a slope, so you can put your m right there. You can solve this, simplify this thing, and you'll have an equation of a line. And then finally, the most useful is y, or what do they call it? They call it slope intercept form. And this is the one you should be mostly familiar with because it is y equals mx plus b. This is the most useful because you can just look at it. One, you can just look at it. You know your starting point is wherever b is, and you know your slope is your rise over run. So you go to your starting point and you follow your slope rules and rise this much and run that much and make your second dot, and then you've got your line. So we'll show you more about that. But another reason this one is most useful is because of our calculators. When you hit this button right here, we have the y equals button. And I have a bunch of stuff in here that I'll clear out real fast, but notice this is y equals. This is y equals. This is y equals. This is y equals. So our calculator is set up for this already. It's already set up in the y equals mx plus b form, and so if we can manipulate these other two equations to y equals mx plus b, well then we can type them into our calculators and see them get graphed, like so. So this is why y equals mx plus b is so important. So these are the three forms that you may see a line come in. In all of these forms, you can isolate the y using your algebra skills. Isolate the y on the left-hand side, and you can manipulate these things to the right-hand side and simplify. And of course, you'll end up with an equation y equals mx plus b. I would recommend if you can and you're comfortable with that. Personally, I always change all of my line equations into y equals mx plus b because I find that that's the easiest to work with and know what I'm doing. So let's make some sense of this. My marker is fading fast, but here we go. Ooh, that's bad. And I can't draw straight, so don't worry about that. It's technically a straight line. There's x, there's y. So, and we have the equation y equals mx plus b. So, like I said before, b is our y intercept. And m is our slope. So, how do I graph? So if someone gives me an equation, say y equals, I don't know, 1/3 x plus, how about minus 2. Okay, so here I'm going to look at here I notice right off the bat that I'm in the form of y equals mx plus b, y equals mx plus some b. And so I'm already in the form. I can just get to it. So I'll go to the y-intercept. It's -2 in the y. -2 in the y. So there's that spot. And then, of course, I go up 1 and over 3. Up 1 and over 3. Up 1 and over 3. And there you can see with my connected dots that I'm slowly forming a line. So this is how we graph lines in our standard coordinate plane. I think it's important to notice we have some problems that we'll work on, but I think it's important to notice that these are kind of circular. They're circular in the sense that graphs lead to tables of values. which leads to an equation, which leads back to graphs, or vice versa on all of these. So there's graphs, equations, and tables of values, and they all go together. So if you have one or two of these, you can find the third. If you have one of these, you can make the other two, for that matter. So let's talk about that real quick. We had our equation, well, let's do a different one just to simplify my life a little bit. Of course, I know you guys love it when math teachers take it easy on themselves, because it never seems like they're being taken easy on you. But let me show you how these things lead to tables. So we have our favorite equation, y equals 2x plus 3. We go to 3 in the y, up 2 over 1, up 2 over 1. This is our slope. If I want to go the other direction, it's down 2 over 1, down 2 over 1. This will help me make my line straighter. Okay, so there's all the values of y equals 2x plus 3. And to show you that those are all the values, let's consider a table here. And I will make my table like so, and I'll say this is x and this is y. And so we'll say 0, 1, 2, 3, 4. And so what is y if x, so I have y equals 2 times 0 plus 3, which is equal to 3. So this is 3. So if x is 0 right here, then y is 3. Sure enough, there it is. I have 2 times 1 plus 3, which is equal to 5. And notice I go to 1 in the x, and sure enough, there I am at 5 in the y, so I'm on my line, so that's good. So this is 5. Here I have 2 times 2 plus 3, which is 4, plus 3, 7. So here we are, 7. If I go to 2 in the x, sure enough, I'm up at 7 in the y. So here we go. This is how equations, graphs, and tables all work together. 2 times 3 plus 3 is 6, so 9. There we go. So you can see I've made a table, I've got a graph, and I've got an equation. All those things are speaking to each other nicely. So let's take a look at one of our practice problems from our exam that we have. I know that on our exam, one that had a table right off the bat. If you take a look at number 11 here, you'll notice that we have a table of values. Student studying motion observed a cart rolling at a constant rate along a straight line. The table below gives the distance, d feet. The cart was from a reference point at 1 second intervals from t equaling 0 to 5 seconds. So here's t equaling 0 to 5, and this is the distance that the cart went. What is the following equation represented between d and t? So basically, we've been given a table, and I've told you that if you have a table, you can find the graph, or you can find the equation. So in this case, we need to find the equation. So I have the table. And I don't need this entire table. I'll just, for simplicity, we'll label that x and y. X is 0, 1, 2, 3, 4, and the values that went with it were 14, 20, 26, 32, 38. So I didn't copy the whole table, but it's not necessary, and I will show you why here in a moment. If you've been given a table, or for that matter 2 points, And let's go here, 0, 14. Call that 0, 14, and then we'll call this 1 and 20. So there, now I have 2 points, so you can see this table is leading to a graph rather easily enough. You just start plotting the points and connect the dots. But how does that lead to an equation? So first off, we need that m formula, right? We need m. And it's rise over run, so we know we're doing the y's divided by the x's, which is the run, right? The rise divided by the run. So I'm going to label these points. I have point 1 here is x1 and y1. Point 2 is x2 and y2. So now I've labeled everything. Now I just plug and chug. So what I'm looking for is y equals mx plus b, right? So I need the m. Actually, if you look at my graph, I already have the b, right? We have the b, it's plus 14. And if you look at your answers, right off the bat, you can narrow it down to 2, because C and A have plus 14. So now we just need to figure out what our slope is. And we're going to figure out our slope using this guy right here. So y2 is 20. Y1 was 14. And we're dividing it by x2, I'm sorry, which is 1, and x1 is 0. So 20 minus 14 is 6. 1 minus 0 is 1. And so we get m to equal 6. 6. So now that I have my m, I can simply plug this into my equation. Y is equal to 6x plus 14. I look at my equations, recognize that I subbed x and y for d and t, and sure enough I have answer C. D is equal to 6t plus 14. 6t plus 14. So C is our answer to this equation. So notice tables, graphs, equations. Given one, you can find the other two. There's another problem in our practice test that is rather similar. Comes in story problem form. It does not have a table. If you look at number 16 here, that's right, if I can zoom in on it a little bit. Here we go. A car accelerated from 88 feet per second to 220 feet per second in exactly 3 seconds. Assuming the acceleration was constant, what is the car's acceleration in feet per second from 88 feet per second to 220 feet per second? So you may read this problem and be like, oh my goodness, I didn't know I was going to have to do all the physics. But really it's just recognizing that you're looking for rise over run. It's not a particularly difficult problem, but recognize that at time 0, right, you're going 88 feet per second, and exactly 3 seconds later, 3 seconds, you're going 220 feet per second. So using these 2 points, using the point 1 as 0.88 and point 2 as 3.220, I can calculate a slope. I can calculate a rate of change, rather, right? That's what they've been calling them. So I say m is equal to y2 minus y1 over x2 minus x1. If you have trouble remembering this, it's not hard, because it's the rise over the run. So memorize rise over run first, and then make sense of what that means in your formula. In this case, so point 2 is this one, so I have 220 minus 88, okay? And then, of course, here I have 3 minus 0. I'm looking for the rate of change on this thing, so I'm not keen on doing arithmetic, so I'll do the calculator. This is 132. 3 minus 0, I got that one. That one's 3. 132 divided by 3 is 44. So this is equal to 44 feet per second this is our final answer. And then, of course, we hope and pray when we look back at our answer sheet that, sure enough, there it is, 44 feet per second. So this should be a good reminder of slope, rise over run, how to calculate it when you have been given two values, how to read it otherwise when you're trying to graph it. Okay. Throwing some stuff away here. All right, so that was our formula. Welcome back. Slope, rise over run. It's represented in story problems. We just did two story problems. You're going to see tables, you're going to see graphs, you're going to see equations, and how the three of those all relate to each other. Keep in mind these two right here, horizontal lines, are in the form of y equals something. If you have y equals 0x plus b, keep in mind that 0x is zero slope, so you have a horizontal line, right? A horizontal line, whatever the b is in your equation, just draw a straight line across your Cartesian plane. And for vertical lines, you're going to have x equaling something. X has to equal something. Y can't equal anything. Think about what that would mean. All the y's would be the same. If it's a vertical line, right? I'm sorry, all the y's would be different. Vertical line, you'd have x equals 2, and you'd have the point 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. A vertical line straight up your graph. So that's slope. If you guys have any questions, please holler at me. inspiredclassroom.tim@gmail.com. The next thing we're going to talk about is parallel and perpendicular lines. Once you understand how to graph lines and get the equations for lines, parallel and perpendicular is not very, very difficult. The definition of parallel, right, is lines that never intersect. And therefore, in this case, you'd have to imagine they'd all have the exact same value for slope. Look at these two parallel lines that you see down here. Line 2 is gradually going up. Line 1 is following in the same pattern, also gradually going up. The only difference between these equations, when you see these equations, is going to have, in the y equals mx plus b, it's going to have a different b. But the m is going to be exactly the same. So here we have parallel lines. On the other token, we have perpendicular lines. And notice the slope here. The slope here, you can always tell slope when you're looking at lines. Just a quick reference, this one's going to have positive slope just because of the way it's running. It's going from left to right, it's going up in that direction, just like the way we read. This green line has a negative slope. It has negative slope because it's going down from left to right. So down our plane, that's negative slope. If you look at my example here, if I can get out of the way, we had y equals 2/3 x plus 2 and y equals negative 3/2 x plus 5. These lines are perpendicular. Now these are not the equations of the lines I have shown here, but this is just a quick example of what perpendicular lines have. So they have to have the opposite, what's called the opposite reciprocal. Excuse me. And so notice my slope in this equation is 2/3, positive 2/3. And in this equation, my slope is negative. It's negative, so that's telling me I'm going the other direction. And the fraction, the rise over the run, is flipped. So my rise over run over here is 2/3. Here it's down 3/2. So that you just flipped the fraction. So perpendicular lines have negative reciprocals, is what we call that. And let me show you quickly in my calculator just some parallel and perpendicular lines. So we'll Oops. Oh, I hit the wrong button. Nope. We're good. All right. So let me show you in my calculator a couple of parallel and perpendicular lines. So here I've graphed y equals 2x plus 3, and I can graph y equals 2x, how about minus 4? So there was my first line, and there's my second line. Hopefully you guys can see that, but they're parallel. They never intersect. Same lines. Now I can come up with a line that is perpendicular to both of these, right? Since they're parallel, one line that will be perpendicular. I got to flip my fraction, so the denominator of the 2 is actually a 1. So now I have negative 1/2 x, and I'll just leave it at that. There you go. There's my perpendicular line to both of those, right through the origin, because I didn't give it a b, so the b is 0, 0. But notice the negative slope, and it is hitting these parallel lines, both of them at a 90-degree angle. So that's the skinny on perpendicular and parallel lines. Parallel lines have the same slope, but different y-intercepts. Perpendicular lines, the intercept doesn't matter much, but the slope has to be the opposite reciprocal, or the negative reciprocal. Not just negative. If I graph a line negative 3x, let's see, negative 3/2 x plus 1, there's my line. There it is. And if I want the perpendicular line to it, I have to flip my fraction, change the sign, and there it is. There it is. So positive slope, negative slope. You can look at your graphs and know that right away. If you guys have any questions about using your calculator or graphing parallel and perpendicular lines, please shoot them at me, and I will respond as fast as I can. Let me know if you guys have questions about parallel or perpendicular lines. The next thing that we see could be useful in our Cartesian plane is the distance formula. So looking at this guy, it's derived from the Pythagorean Theorem. Okay, right? So a squared plus b squared is equal to c squared. So if you want c, right, c being the hypotenuse, we haven't talked much about some of our plane geometry yet, but the Pythagorean Theorem, if you want c is the hypotenuse. It's the square root of a squared plus b squared. And so if you look at this, look at our Cartesian plane here, I have point 1 graphed right there, and then I have point 2 graphed right here. And if I want to know the distance between these 2 points, well, I simply take the x values, the difference of the x values, right? That'll give me this leg of the triangle, and the difference in the y values will give me this leg of the triangle, right? And then I can use the Pythagorean theorem. So x squared, or x2 minus x1 will give me that value. Square it, add it to y2 minus y1, square it, add those together, take the square root, and I can find the distance between 2 points. So let me do that for you in an example real quick. We'll put the distance formula to work here, so we can give it some context. Number 2. And I'm gonna graph in green. I like doing math with some color. So there's my Cartesian plane. my x, there's my y. So let's go to this point. 1, 2, 3, 4. 4, 1, 2, 3, 4, 5. How about 4, 5? To the point 4, 5. And I want to know how far away that is from the point 3, -3, -3. How about that? So here we are. Here's these right here. And so I need to find the distance. So I'll draw my triangle. Draw my triangle. And this is going to be y2 minus y1. And this is going to be x2 minus x1. Because this is my x's. And these are my y's. Our formula was d is equal to y2 minus y1 squared plus x2 minus x1 squared. So this distance is x2 minus x1, and this distance is y2 minus y1. So y2 is 5. 5 minus y1. y1 is -3. So a -3 is actually 5 plus 3, so that's actually going to be an 8. An 8 in the y, so this is an 8. So this part, so we'll simplify this. This part is an 8. Move that up. So I have an 8 squared, right? Plus, and then we'll do my x's. So my x's are 4 minus, again, a -3. So 4 plus 3 is actually 7. So I have a 7 squared right there. This is equal to 64 plus 49, which is equal to 64 plus 49 is 113. 113. And I would actually stop right there. You can take the square root of this number if you have to. It's not going to be a nice number. 113 is not a perfect square. It is between 10 and 11. But this is the actual distance right here. This line right here is 10.63 and some change units long. So our D is equal to, which is equal to 10.63. There, you can see D is equal to root 113. So that's the distance formula in action. I haven't seen it in any ACT practice problems that I've done, but it is fair game, and it's certainly something that could come in use for you if you need to do that, and recognize that it was derived from the Pythagorean Theorem, right? You need a right triangle, but it's the difference in the x's, difference in the y's, squared, add them, sum them, square root, and you'll have your distance between 2 points. Not too shabby. Once again, I would refrain from trying to memorize that formula as opposed to making sense of it. A squared plus b squared equaling c squared is pretty standard, pretty easy to remember. So the distance formula shouldn't be too much trickier than that once you recognize that it's just a squared plus b squared equals c squared. The distance formula. We also have the midpoint formula. I don't know if I need to show an example of this one. I have one on my PowerPoint slide here, but you may need the midpoint at some point. Once again, I would refrain from trying to memorize this as a formula, but to make sense of it. So what is actually happening here? The midpoint. If you can remember how we calculate averages, right? If you want to average your test scores, say, you add up all of the scores you got on your exams, you divide by the amount of exams that you took, and that's your average score for those exams. So hopefully that makes sense, the finding the average. And then when you look at this, you notice that it's just an average, right? So if you look at the 0.41 and 10.5, they've been graphed for us on this nice picture that I found. If we want the x's, we simply take 4 and 10 and we add them together. We get 14. We divide by 2 and we get 7. 7 for the x's. Similarly, for the next point, if we want the y's, we average them as well. So it's 5 plus 1 is 6, divided by 2 is 3. So there you have it. It's as simple as that. It's less about memorizing this sort of thing, but understanding, right? The midpoint is going to be the average of the x's and the average of the y's. So it's as simple as that. Add them together, divide by 2, because that's how many you added together. So this is the midpoint formula. Very straightforward. So here we are. This is the last section that I really have for you. Conics and families of functions. I talked to you last time about families of functions, recognizing y equals mx plus b, or the parabola, right? Y equals ax squared plus bx plus c. We have the cubic function of x cubed. We have a square root function, a natural log function, and of course the exponential function. Some y is equal to some constant, some b to the x, some other number to the x power. So families of functions, I talked about those a little bit last time. It's good to get used to recognizing those, right? Notice the powers. There's the first power, the second power, the third power. This is actually to a half power. And then this power is always changing. And then we have our logs, of course. But notice the families of functions. For conics are a little bit tricky. It's been a while since you probably didn't spend very much time in your high school algebra classes or geometry classes working on conics. I know I didn't. I know I had an introduction to them. These formulas can be pretty overwhelming and scary looking. I'm going to show you quickly how to solve some of these problems. First off, we need to be comfortable with our different conic shapes, right? We have a circle, and this is the formula for a circle. You will generally see circles of the equation x squared plus y squared equals r squared, which happens to be derived from the Pythagorean Theorem. But notice that it's equal to some radius squared. And then, of course, you're going to be centered. Your center of the circle is h and k. Whatever these values are, this is the center of your circle, and then you go out from there. In all of these formulas, the center is the most important thing. The center of the parabola, the center of the ellipse, the center of the hyperbola. It's all hk in these formulas that you see here, hk. Notice too that this one is equal to some r. It's the radius. The circle is equal to some r. The parabolas, I wouldn't worry too much. I don't see parabolas in this form very often. It happens from time to time. You'll usually see them in that ax squared plus bx plus c form, generally. But these ellipses and these hyperbolas, these I want you to notice that they're equal to 1. Equal to 1 on both sides of me here, whether it's the horizontal axis or the vertical axis. They're both equal to 1. The difference between these formulas happens to be the plus sign. The plus sign for ellipses, which you see right here and right there, the plus sign. And then, of course, in the hyperbola down here, you can see that we have a minus sign. So they're both equal to 1. Or both of them have equations that are equal to 1. It's really depending on whether we see a plus or a minus. is going to define what shape we're looking at. So I have a couple of practice problems here. Keep in mind on the ACT test, it's not going to be too detailed. So I'm going to show you what it would be like if I was given these equations and I had to graph them. So hopefully this will be useful to you. It is not. It's kind of weird. It takes some practice. But it's very possible. So here I have an equation. So first thing I want to notice is I have a plus sign and it's equal to 1. So I have a plus sign. A plus sign told me that it was an ellipses and it's equal to 1. So I need to get the center. The center is, of course, is important. So here I'm centered at the point 1, 1, 2. 1 in the x, and notice all the x's it tells you. It's telling you this is dealing with x, this is dealing with y. So we're going to go 1 in the x, 1 in the x, and 2 in the y. So there, right there is my center. So that's the most important thing. Second most important thing is recognizing that what squares are these? What squares are these? Well, 1 is just 1 squared, and 4 happens to be 2 squared. So once I find my center, it's pretty easy after that. Once I find my center, I know I'm doing an ellipses because it's a plus sign and it's equal to 1. I've figured out my values on the bottom of these fractions right here to what their square values are. So once again, looking at the x, I'm going to start at my center and I'm going to go 1 out, 1. Only 1 out from my center. So I'm going to add a couple of dots right there. And then I'm going to go to my y, and I'm going to look at my value, and it says 2. So I actually go 2 up in the y. So there's that from my center, of course, from my center. And so there you have it, right there. There's my ellipse. Once I have those spots and my center all determined, I can just connect the dots, and sure enough, there it is. For another example, we can come over here, and I still have x over here and y over here, so this is going to be 1 squared, and again this will be 2 squared, but now my center has changed. My center is different. So here I'm still at 1 in the x, but now I'm at -3. So the formula says y minus k, right? hk is your center, so this k is actually -3. So 1 in the x and -3. So there's my center. There's my center right there. And then I simply count. Here I have 1 squared, so 1 in the x. So in the x, horizontally, I come out 1. And in the y, I have 2. 1, 2. So there's that. And then, so there, right there is my ellipses. Right there is my ellipses that I have. So that's solving ellipses. So now let's consider a hyperbolic equation. Notice here I'll bring these in so we can observe the differences in equations. But notice the minus sign. Now I have a minus sign. So this one is a little trickier. But it's still very doable. So here I have a y squared, so it's y minus 0. So in here I have a 2, a positive 2 in the x. So I'm going to go find my center, right? Find my center, so 2 in the x and 0 in the y. So there's my center, right there. These squares, this is 4 squared, and this is 3 squared. So here in my x's, I'm gonna draw a square that I'll connect, and show you the points to what a hyperbolic function looks like. But in the x, I'm going to go 4. So 1, 2, 3, 4. So to -2, and 1, 2, 3, 4. So there's that spot. And then in my y's, because it says y, I'm going to go to 3. So 1, 2, 3, 1, 2, 3, Right, and I'm gonna draw a square to connect these things. Right. So there's my square, and then these ones are always easier with a bit of a straight edge. So I'll do my best with a piece of paper here, but we wanna draw lines right through the middle of our box. Extend them outwards. And we have to decide, is this thing going to come down this way and up this way, or is it going to go out this way and go out this way? So with these hyperbolic functions, it's easiest to tell because the x is first. So the x is first, so that means we're going to come around here, we're going to touch that spot and jet around that direction. So this is my hyperbolic function that you see here, graphed in our Cartesian plane. So one final example of this, because this takes some practice, it takes some getting used to. It's certainly not difficult, but it's recognizing the pieces that you have, right? So here I have, notice before I had x first, and now I have y first. So now I know that I'm going to have some graph going up and down. I have my minus sign, so I know it's a hyperbolic function, hyperbolic. And it's equal to 1. So I go to my center. My center is 2 in the x, 1 in the y. Right there. There's my center. I count 3. 3 squared is 9. So 3 up in the y. 1, 2, 3. From my center. From my center. 1, 2, 3. There it is. And 2 in the x from my center. I draw my box. I draw my lines, of course, and then I observed that over here, right, x came first, so I went in the x direction with my graph. Here I'm noticing y is coming first, so I'm going to follow my graph down, touch my point, and shoot off in that direction. Similarly, here, touch that point, and shoot off in that direction. So there's my hyperbola function right there, hyperbolic function. It takes quite a bit of practice to get used to. Here's the answers to those equations. There's this one, right? And of course there's that one. It takes some practice, it takes some getting used to, but it's very doable, and it makes sense. It makes more and more sense every time you do it. So our calculator will not help us graph these sorts of things because our calculator will only graph y equals stuff. So it won't help us with this, but the ideas are not too difficult once you play with them for a little bit. I found these worksheets at mathaids.com, so if you'd like to get your own practice problems, they have plenty of stuff there for you to be able to practice these sorts of things. All right. I think that's all I have for you guys today. It was a quick rundown on coordinate geometry. There's obviously still more things that could pop up, but I hope that this served as a good refresher for some of the topics that you may run across on the ACT exam. My name is Tim. If you have questions or want help, please feel free to email me at inspiredclassroomtim@gmail.com. I will do my best, and hopefully we'll hear from you soon. Have a good day. Thank you.